We are starting the session. This is the Milky Way session number 2. And we are starting with Casey Lam from the Carnegie Observatories. He's going to talk about the finding black holes with microlensing, the current and future prospects. Thank you, Casey.
Thank you. Can you hear me? Okay, great. Thanks everybody for sticking around for the last session. Let's get right into it. Astrophysical stellar mass black holes are formed from the deaths of massive stars. And they're important to study because they tell us a lot about the death and evolution of massive stars. So these are some properties that we would like to understand about massive star evolution and interaction. The problem is, it's hard to answer these questions without understanding the population of galactic black holes. We don't understand a lot of things about the galactic black hole population, including very basic things like as the total number of black holes in our galaxy. And the reason for this is because the black holes we know about in our galaxy are mostly X-ray binaries like that, or from gravitational wave black hole mergers outside our galaxy as detected by gravitational wave detectors. And so because our sample is biased towards a very rare population, the galactic population, which is actually expected to mostly be isolated black holes, as shown here on the right, this is why we can't answer a lot of these open questions about massive star evolution. And so we need to find isolated black holes which are representative of the broader population of galactic black holes to answer these questions. So the reason why isolated black holes are hard to find is because they don't have a companion to interact with. And so gravitational lensing, gravitational microlensing is the best way to do this. So, there's a lot of microlensing in the last session, but I just want to highlight that there are two effects in gravitational microlensing. There's the temporary brightening, which is called the photometric microlensing effect, and a temporary change in position, or the astrometric microlensing effect. And so the reason why these are important is because, as was briefly mentioned earlier, if you only have that temporary brightening, which is what's illustrated here on the right, you cannot measure the mass of the lens, because from this temporary brightening alone, you measure two parameters, this TE, which is the time scale of the event, or this pi e microlensing parallax, which encodes the relative distance to the thing that's doing the lensing and the background source of light. But if you can measure this temporary change in position, this astrometric shift, you can directly measure the Einstein radius, theta e, which is the angular scale of microlensing. And if you can do that, this here shows the unlensed motion as this black line. This colored line shows the astrometric deviation. You can see that it doesn't fall on top of the black unlensed line. That difference is the astrometric deviation, and that gives you that measure of this Einstein radius. And so if you can measure this astrometric shift, this is the formula for how you measure the mass of a lens with microlensing, then you get this parameter here, the Einstein radius in the numerator, the relative distances from the photometry, and then you can measure the mass of the lens by breaking that photometric only degeneracy. Okay, so that's the framework of how we can find isolated black holes. So how this works in practice is you have a sample of photometric microlensing alerts produced by various microlensing surveys, for example, either MOAA, as Naoki talked about, or OGLE. And so these surveys produce typically about 2,000 alerts per year. And about 1% of those should be due to black holes. So the thing is, we cannot astrometrically follow up 2,000 objects a year, so we have to be careful and pick things that we think will likely be black holes. And the time scale of a microlensing event is proportional to the square root of the lens mass. So this suggests if you want to look for black holes which are massive, you should look for long time scale events. And so in practice, what we do is when we see these alerts, we sift through them and say, okay, what's long? We say long is usually longer than 120 days. And then after that, you go and follow up these good black hole candidates by getting high precision astrometry. And the best way to do this right now is using the Hubble Space Telescope. There's another difference between photometric microlensing, the change in brightness, and astrometric microlensing, the temporary change in position. The astrometric deflection decays a lot more slowly than the photometric magnification. And so that means is the change in brightness, you go from peak brightness to baseline brightness in about 1 time scale. But the astrometric deflection takes about 10 times as long to decay away. So your maximum deflection versus no deflection is a lot slower to go away. And that means you need to have a very long observing baseline. So typically, this means you need about 5 to 10 years of monitoring. Okay, maybe that's all sounds crazy, but it works. I just want to advertise that we can actually find isolated black holes, and we did this recently with this object, OGLE 2011 bulge 462. And so by combining ground-based photometry and then following up with HST WIFC3 UVIS, we found a 6 solar mass black hole 1.7 kiloparsecs away at a relatively slow transverse velocity of 40 kilometers per second. And so down here, this is just highlighting the HST astrometry taken in 2 filters. That's what the red and blue data points are. The change in position versus time and RA on the left and DEC on the right. And so this maximum deflection is about 2 milliarc seconds or less. So it's very small, but this is well within HST's astrometric precision. And so the other thing you can do is there was 4 other candidates that were non-detections. And so by combining the single detection with the 4 non-detections, by accounting for the selection effects and the timescales, we're able to show that this 1 detection is consistent with a population of 100 million galactic black holes. So it's not a measurement per se because the uncertainties are still so large with a small sample, but we can show that this 1 detection is consistent with 100 million black holes. And so we're starting to get at direct measurements of the number of black holes in our galaxy, which is one of these unknown quantities. Okay, so if you remember one thing from this talk, you can take away that we can find isolated black holes. We've done it and it works. But there are some things that are not ideal about this. First of all, following up high precision astrometry with HST is very expensive. Each astrometric measurement takes about an hour or 2. And so that severely limits how many things you can follow up. And so that is also the reason for this cut on only selecting long duration events. This is another problem because it throws away a lot of black holes. And just to kind of quantify this, these come from microlensing simulations. And here on the left, I'm showing the distribution of timescales as a function of what the lens is. So this dashed blue is star lenses, orange is white dwarfs, green is neutron stars, and red is black. Red is black. Red is black holes. And so on the right here, this is showing what's on this plot, except it's the fractional contribution of each lens type at a time scale. So you can see at long time scales, your contribution from black holes is very high. So that's why we were selecting for long duration events in the first place. If you're following things up, and you have limited resources, you want a high purity. But look at this plot. So the purity is highest, say, after like 200 days. If you look here 200 days and only select here, that's where the black holes are, you can see that you're chopping out in number a lot of black holes. And so this is throwing away, number 1, a lot of black holes, but number 2, this might introduce selection effects because, for example, if black hole mass is correlated with kick velocity, this might introduce some type of bias that we're not aware of. And so it's important to get all the black holes in a biased sample. Okay, so this is the problem, but Roman is going to be awesome because simultaneous photometry and astrometry over a wide field of view is going to kind of take away this problem because now you're no longer limited to these very small and biased samples for follow-up. You're going to get the photometry and astrometry at the same time. And so you don't have to say, oh, I can only do 5 objects a year. Thank you. You're just going to get all the photometry and astrometry at the same time. So Roman's going to be awesome. And so just to leave with some numbers, from the time domain survey of the galactic bulge, Penny et al. Predicted about 3 × 10⁵ microlensing events over the survey. And so 1% number, that's about 3,000 black holes. The question, though, is how many of them will actually be characterizable where you can get the mass and velocity and so forth. A recent paper by Sajidin and Sahu think it's only going to be 5 to 25. And, versus 3,000, that's very small. And the reason for this is because in the current notional survey, there are 6 galactic bulge seasons, 3 at the beginning, 3 at the end. And there's this ginormous gap of 2.5 years about in the middle. And so this is like a microlensing light curve. You don't see the fall here, and you would miss a lot of that astrometric shift. And so the thing is that, oh, what happened there? Okay. The thing is that you want to do to be able to actually characterize these black holes is to fill in that 2.3-year gap. And so in Dan Huber's talk earlier, a couple of days ago for the Core Community Survey Definition Committee, they were talking about how in the bulge seasons for Roman during the non-main parts of the galactic bulge time domain survey, filling in 1 observation per day would kind of be like the overguide. This is the plug for we should do the overguide, because if you can get 1 observation per day, you can get 0.3 milliarc-second astrometric precision by stacking over 10 days. And that is important because here I'm showing the distribution of maximum astrometric shift versus number of black holes. And the maximum astrometric shift for black holes falls off strongly between 0.3 milliarc-seconds and 0.8 milliarc-seconds. So if you only get 1 observation every 10 days, you're here, and you're going to miss most of the black holes. So this is important to get 0.3 milliarc-second astrometric precision, because that way you have a hope of detecting more of these black holes. And it's also important for getting good photometric coverage, because as I showed in the previous slide, if you don't cover the light curve well, you're not going to be able to measure the photometric parameters, which are also important. And so to conclude, characterizing the galactic black hole population, particularly the isolated black hole population, is really important for understanding a lot of different astrophysics of massive stars, how they die, and how they influence their environments. We have now detected an isolated black hole with microlensing. Roman's going to do an awesome job, especially if the observing gaps are filled. And since there's some discussion time, if people are not running away to go home, these are just some other things that I'm thinking about / worrying about and would be happy to talk about. So thank you.
The question here, thank you.
Okay, Casey. So, for the free-falling planets we just heard about, we're interested in getting, simultaneous observations either from Euclid or from the ground. And it seems like, potentially that same sort of strategy without the simultaneous part would help with characterizing these light curves outside of the regular Roman seasons. Have you looked at what sort of ground-based telescopes might actually be able to get good enough data?
Yeah, so I was very interested to hear about the Subaru 100 days time, although that sounds very competitive to get. There's also Prime, of course, but there it would miss a lot of the fainter events. And so I think that is another thing to think about more about. But I think right now it's like Subaru and Prime are kind of big ones in mind. LSST also, as Etienne said, but the coverage there in the bulge might not be high enough cadence, because I think right now that's about once every 5 days. Yeah.
So in one of our LSST proposals, some of the reviewers suggested getting the CTIO 4 meter, where you can maybe get more observing time than LSST.
Sorry, CTIO?
4 meter?
Uh-huh.
So like the deck cam or whatever. I don't know if it's still beyond the telescope. But.
Oh, sorry, I couldn't quite hear over the fan.
Deck cam or DE cam, I don't know what it's called, but I'm not sure if that's still going to be on the telescope when Roman's flying.
Other questions? There is a question there, and then in the back.
So, in addition to the data point, and as for the strategy of observation with Roman, in addition to the additional point of season, would you see an interest also in changing the free season at the beginning, free season at the end, with the gap in the middle with something different for getting black holes?
The question is whether changing the field versus.
No. Changing the nominal strategy now with the free season at the beginning and
Oh.
the free season at the end with a different one. Would that be beneficial for the black hole?
I see what you mean. Yeah, so we'd like to have the densest sampling all together. So it would kind of be the opposite. Like you would maybe like to have the 6 highest cadence seasons in the middle and then 2 each sparser cadences on the other side. But I don't know if that will, how much that will muck with the exoplanet requirements. Because if you have 1 day cadence at the last 2 and the first 2 seasons, I don't know if that will be good enough for their proper motion requirements, but I think if that would be possible, that would also be a good strategy, because that way you could cover the astrometry and photometry more in a bigger continuous block.
Hi. So related with Dave's questions, which information is more critical for the filling the gap, either parallax signal or astrometric signal?
Which is more important, photometric or astrometric?
Yeah,
So
for the reason to filling the gap, yeah.
yeah. In ways, photometry is more important to have at a higher cadence because the astrometric signal moves more slowly. So you could imagine, say, if you want average of 0.3 astrometric precision over 10 days, you could put all the observations in 1 day versus spread them out once every 10 days. But having them out every 10 days is better because that way you can also get the photometric coverage.